You see the slide? Okay. So I understand you can see the slides. Okay, good. Right. So SIL selection using exSILentia. So last week we did the actual SIL determination. So this will follow on from that one last week, and we will do this in two phases. We will do the presentation first of all, followed by a demonstration using exSILentia itself. So my name is Gandy. I'm responsible for Exeter's global business development. I have 37 years experience in safety and controls. Primarily my background was in software and hardware, designing some of the earlier safety systems that were used by Industrial Control Services, ICS. Now it's part of Rockwell. I've been associated with the ISA as well as other UK bodies. I'm a member of the MBAs in the UK, and I've also published papers on managing risky projects, which was risk management, and conforming to operation and maintenance requirements. If anybody wants to contact me after this session, this webinar, you feel free. My email address is asgandy@exeter.com. So a little bit about Exeter. We are a global network of companies. We provide functional safety, cybersecurity, and alarm management services, plus also we provide tools to help support the full safety life cycle. Our main offices are located in the US and Germany, but we have other offices around the world, South Africa, Asia Pacific, and Latin America, as well as North America. So looking at our industry focus, we serve what we call manufacturers, the OEMs, where we do management support, development support, and certification, as well as provide tools to help with the design of safety components or safety products. That also includes looking at these products from the cybersecurity point of view. For system designers, we can provide functional safety management setup, so we can help you set up your processes and procedures. We can provide templates, also with SIL verification, and the tools to help support that. For the end user, we can do SIL determination and device selection and SIL verifications, as well as provide the associated tools to support that on both functional safety and alarm management, as well as doing cybersecurity assessments as well for end users. The tool that links all of this together is exSILentia, and some of you may be familiar with exSILentia, some of you may be using exSILentia, or this may be new to you. From an engineering contractor's point of view, it helps with being able to do the designs for safety instrumented systems and safety instrumented functions. There's also competence development. We provide training through our functional safety engineering courses for the Certified Functional Safety Expert and Certified Functional Safety Professional. We are associated with the CFSE board that monitors and manages that separately. The main industries are automation process industries. We're also heavily involved in automotive as well as nuclear. So looking at functional safety, the main standard, the umbrella standard as it's called, is the IEC 61508. And this standard came out in 2000, first edition. There was an updated edition in 2010. And basically this standard is not prescriptive. It doesn't tell you how to do things. It tells you what you need to do. So it's more of a performance-based standard. And that standard spawned into three separate standards, or known as sector standards. There's the 61513 for nuclear, the 62061 for machinery, and for the process industry sector, it's 61511. So we're looking at 61511, where we target end users and integrators in process industries. this covers the entire safety instrumented life cycle, safety instrument system life cycle, and effectively there's three main phases. There's the risk analysis phase, where you do your risk assessments, you determine what your hazards are, what you need to protect against, and look at your risk reduction and what you need to achieve in terms of targets. And this is usually based upon the company's risk criteria. How much risk is the company prepared to accept and take? And then you go into performance-based design, where you have your safety requirement specification that then determines what your safety instrumented system is going to look like in terms of the safety instrumented functions. How many of them are there? What are they there to protect against? And also what associated risk reductions are they going to achieve? And then you get into your operations and maintenance life cycle, where the system is running for its desired, what we call mission time. So again, performance not prescriptive. For end user applications, end users aren't typically certified, and normally what happens is they require functional safety assessments to be done by third parties to provide independence and no bias. And that's where we come in a lot. We do a lot of that type of work. So looking at the functional safety life cycle, as we mentioned already, we have the hazard identification. So what can go wrong? This is where you do your process hazard analysis and your hazard and operability studies. Then you can do your risk analysis, SIL selection, usually doing it through a layer of protection analysis. In other words, how bad can it be? So what do you need to do in terms of how many layers of protection? Your safety requirement specification, what needs to be done. This is where you document all the SIFs, safety instrumented functions, for the safety instrumented system. And this is a detailed requirement specification. In there, as we saw from last week's SIL determination, you include what your target SILs are that you're looking for each instrumented function. And bearing in mind that a safety instrumented system doesn't have one overall safety integrity level. That's something that needs to be understood. The individual SIFs, the individual safety instrumented functions, will each have a SIL level assigned in terms of how much risk reduction. And these won't all be the same. You'll have different SIL levels for different functions depending upon the severity and what they're trying to protect against. And then following that, you do your SIL verification. So this is where you've done the design, and now you're going back to determine, okay, was the design done according to expectation and requirements? So how reliable is it going to be? And then you get into your normal operation life cycle of the plant and the safety instrumented system. And therefore what you do is you go through your management of change and your mechanical integrity programs. And if you make changes, if you have to replace equipment, what you should do is you should go back and verify that the equipment that you're putting in is actually not going to have a negative impact on the safety instrumented function and will not change its safety integrity level. And generally speaking, when you're designing safety instrumented functions, this is where you would have sensors, logic solver, final element. If you're using SIL rated products or components, then generally you will be able to maintain and achieve the SIL you're looking for. So why does an SIS exist? Well, it is there to manage risk. And as you can see from the top of the line, we have increasing risk, process risk, and then going down below that we have minimum risk reduction. This is what are we looking at to bring the process risk down to a tolerable level. And of course there are different things you can do with that. You can look at the process, you can see, okay, how safe can we make the process? Is there anything we can do there? Design, This is all to do with how the plant is laid out and how the instrumented system is going to be designed. Your basic process control system, how is it going to provide protection in terms of managing the process, generating alarms, any relief systems, such that if you have blast walls, or if you've got a refinery and you're having to store and volatile chemicals or liquids, then you would have blast walls potentially. You would have different areas for storing some of the highly explosive material. There's lots of things that you would do before you start looking at your safety instrumented system. So you can do what we call as ALOP, risk reduction. That's as low as reasonably practical. And that really is determined by the company's risk philosophy, how they view risk, and how much tolerance they have to risk. So that all determines how far the SIS needs to go in terms of risk reduction. So from a safety integrity level point of view, there are generally 4 safety integrity levels, and you specify them with SIL 1 being the lowest, SIL 4 being highest in terms of risk reductions. And generally in the process industry, certainly for 61511, we normally only look at the first 3, SIL 1, SIL 2, SIL 3. It's very, SIL 4 tends to be reserved for the nuclear industry, and also some railway signaling systems require SIL 4. But generally in the process industry, it's SIL 1 and SIL 2, in some cases SIL 3, depending upon the type of hazard you're protecting against. And from IEC 61511 Part 1, Clause 3.2.74 is basically how well the safety function performs its job of managing risk. If we look at safety integrity levels from the types of operation. Now, in 61511 it talks about 2 types. It talks about demand mode and it talks about continuous mode. In 61508 it's split into low demand, high demand and continuous. So there's a slight difference, but in general we talk in terms of demand mode as being less than once per year, or not more than once per year for a demand on SIS. And again, the safety integrity levels are SIL 1, SIL 2, SIL 3, SIL 4. So if you're looking at risk reduction, SIL 1 gives you a risk reduction of between 10 to 100. In terms of probability of failure on demand, and for demand mode, we tend to look at the average probability of failure on demand. We assume a constant failure rate based upon the bathtub curves. If those of you that have done reliability engineering, you'll understand all about the bathtub curve. In the flat portion, we assume that the failure rates are constant. So in terms of the probability of failure on demand for a SIL 1, you're looking at 10 to the minus 1 to 10 to the minus 2. For SIL 2, it's 10 to the minus 2, 10 to the minus 3, and SIL 3, 10 to the minus 3, 10 to the minus 4. So in terms of risk reduction, that's 10 to 100, 100 to 1,000, 1,000 to 10,000, and then SIL 4 is 10,000 to 100,000, or 10 to the minus 5, 10 to the minus 4. So the correlation is that risk reduction is the inverse of probability of failure on demand. For high and continuous modes, we talk about the probability of failure per hour, PFH. And again, for the safety integrity level, SIL 1, it's 10 to the minus 6, 10 to the minus 5. SIL 2 is 10 to the minus 7, 10 to the minus 6. SIL 3, 10 to the minus 8, 10 to the minus 7. SIL 4, 10 to the minus 9, 10 to the minus 8. So those are probabilities of failure per hour. And these tables are available in both 61508 and 61511. So looking at SIL Design Verification, the three things that we look at, or according to the standard, is that you're looking at random failure, or the probability of failure on demand as an average, or the probability of failure per hour. You're looking at architectural constraints, and you're looking at systematic integrity. So basically, PFD average, or PFH, is the random hardware failure rate. And what you look for is it low enough? So, in other words, that's part of the calculation for looking at the SIL level. From architectural constraints point of view, you're looking at either safe failure fraction or hardware fault tolerance. That's SFF and HFT. So do you meet the additional hardware fault tolerance requirements for compliance with 1508 or 1511 for the particular SIL that you're looking for? Systematic integrity, basically that's looking from the life cycle point of view, that's looking at how well has the product been designed and developed. And this is really what I like to call the human factor, because systematic integrity is all about if you've taken every precaution during the design phase of the actual product, you haven't introduced any potential problems or errors that could cause a failure on demand in the field. So from 61508 point of view, there's proven in use, which means that you can, if you have used a piece of equipment or developed and designed a piece of equipment that's been used in many stations that figure out the same application, but has not suffered any dangerous faults or dangerous failures, then you can provide a proven in use justification. But that does rely on you having very good field return data, and usually manufacturers, this is not just warranty returns, it's actual field failure data. You need to have good field failure data to be able to be compliant. Functional safety management, this is what I was saying about how well have you defined and documented and followed your process for developing and producing the piece of equipment. And this also includes software requirements. How well have you defined your software process? How well has your verification and validation been? So all of these things are taken into consideration. And so when you do SIL design verification, you just don't look at the PFD average or the PFH. You have to look at all three together, and they will have an impact on the overall SIL. So from exSILentia's point of view, the SIL verification is called Silver. And this is what we use to determine the SIL integrity level based on 61508 compliance. And we will go through and have a look at the tool like we did last week. But just a little introduction to Silver. It mentioned its safety integrity level verification according to 61508 and 61511. It calculates the safety instrumented function performance parameters. We mentioned already PFD average for the average probability of failure on demand. It looks at mean time to fail spurious. This is something that is important to define and be able to comply with, and needs to be determined when you're doing your SIL determination, and you include that in the software requirements specification, the system requirements specification. The safety integrity level based on PFD average, safety integrity level based on architectural constraints, safety integrity level based upon systematic capability, and risk reduction factor. One of the things that when you're doing SIL determination is if you find that you require a SIL 1 design for your SIF, you really ought to define a risk reduction factor along with that. Because if you just said SIL 1, the designer may just give you a SIF that meets a risk reduction factor closer to 10 as opposed to closer to 100. So if you said, all right, I need a SIL one, but it has to be with a risk reduction factor of 65, that is far more precise, and the designer has to show that he's met that risk reduction factor. If not, as we were saying in last week's webinar, you need to err on the side of conservatism. So if you've not used a quantitative methodology for determining a SIL, then you need to add another safety margin, which is better to say instead of SIL 1, you'd say SIL 2. Because if you don't put the risk reduction factor in, you said SIL 2, then the designers would probably design you a SIF that was closer to 100, which would give you a safety margin on top of your risk reduction factor of 65. If that's what it turned out to be. SIL uses Markov model analysis. We won't go into that in detail, but Markov modeling is widely regarded as being a very good modeling technique, but it's not easy to do, and not everyone can do it. It can also analyze a wide range of architectures. It can be internet-based. We do provide a version of exSILentia that can be run via the web. SIL also uses the exadata equipment database. Now, a lot of people still do PFD average calculations or PFH calculations using spreadsheets, which is fine if you're doing it for a simple architecture, a single architecture, in fact. But you still have to have reliable failure rate data, and that involves being able to get hold of the manufacturer's failure data reliably. Now, usually if the device has been certified for SIL capability, then there would be a safety manual, and in the safety manual there would be the failure rate data you would need to be able to calculate the PFD average or the PFH. But with exSILentia, we use the exadata equipment database. This has basically been developed or accumulated over the past 15 years. It has some 6 billion operating hours worth of data in there, and it is kept up to date regularly. And those who have exSILentia know that every time you fire up exSILentia, if you're connected to the internet, it will go and check to see if there's an update to the database. It accurately accounts for the logic solver configuration in terms of number of I/O channels and modules. And you don't need to have detailed reliability engineering knowledge to actually run the SIL tool. So in that sense, it is very neutral, vendor neutral. It's very fast and precise and flexible. What you can do in exSILentia in minutes will take you hours with using spreadsheets. And especially if you're going to use redundant architectures, because it then becomes even more complicated to do that with spreadsheets. But also, with the spreadsheets, it's also difficult to be able to take into consideration the architectural constraints and the systematic integrity as well. So those are very important things to bear in mind. As I mentioned, the equipment database is updated regularly. So every time exSILentia is fired up, if it's connected, it will check, and it will give you a message to say, do you want to update it to the latest version? That's if you've got your maintenance agreement with exSILentia. That way you will get free updates whenever you go online or whenever you fire up the machine. We do have the Safety Equipment Reliability Handbook. That's product specific, it's for meter based. We do use the failure mode effects and diagnostics analysis technique to look at product failure. This has proven to be a very good methodology, and has actually turned out to be pretty accurate in terms of results from the field data that we're seeing. It's certainly not based on cycle test. Cycle test data is not used at all. We believe that cycle test data can be very misleading, especially for low demand and especially for final elements, because if you have a valve in a low demand mode, it's going to be static most of the time. But if you're looking at it and just doing certification based on cycle testing, then it's not a realistic test for that particular application. So some data that we've seen that have been done, or failure rate data that's been produced as a result of cycle test data, is significantly more optimistic, and in our opinion is misleading and dangerous. We also provide generic types of products based on similar FMETA, and also using industry databases. The generic devices would tend to have slightly more conservative numbers, as you expect. It may be that the actual manufacturer's product data is much more accurate, so therefore it would be better than the generic. The generic is always erring on the safe side. And we can also compare it to end-user proprietary data as well. So if we look at the tool position in the safety life cycle here, it's a little difficult probably to read the graph, but you can see that select is used during the SIL selection and when you're doing the determination. The SRS exSILentia does have an SRS tool that helps you document and maintain your design information for your SIS and for each of the SIFs. And then you have the SIL tool, which enables you to go through and to do the SIL verification. The SIL calculation engine is IEC 61508 compliant. This was actually assessed by a third party and was given the compliance to 1508. So in terms of the silver overview, the safety instrumented function, basically we look at, for a safety instrumented function, it consists of a sensor or sensors, logic solver or logic solvers, final elements and final element. And from the exSILentia point of view, you can have a maximum of 4 groups for the sensor part. You can have various configurations within the group. You can do a per leg with the group, always one sensor and possibly up to 2 interface modules, as we'll see. For the logic solver part and for the final element part, you can have a maximum of 4 groups with various configurations possible within a group, and a per leg within a group. So you can have an actuator and a possibility of 1 interface module and 1 valve. So if we look at it in these terms, here you have the sensor group voting, here you have the final element group voting, and you can see that for a sensor you can have 2 interface modules, and for the final element you can have an interface module, an actuator, and then the valve. And so each of the sensor groups can have up to 3 sensor entries. So a sensor entry consists of a sensor with 2 interface modules and voting options of 1 out of 1, 1 out of 1D, 1 out of 2, 1 out of 2D, 2 out of 2, 1 out of 3, 2 out of 3, 3 out of 3. So you have a diverse options for voting and redundant components. And the components can be selected from the exSIL equipment database. You can also put in your own failure rate data if you feel that you have, if there's a device, for example, that isn't actually listed in our database and there's a generic, but you actually have manufacturer's information, then you can certainly use that. It's a conscious decision by the user to do that. exSILentia allows you to do that. For the final element groups, you can have up to 6 final element entries. And again, it consists of an actuator or can have either an interface module, a valve, or both. the same sort of voting options you can have. You can have 1 out of 1, 1 out of 2, 2 out of 2, but then you can have 2 out of 4, 4 out of 4, 5 out of 5, and 6 out of 6. So again, all the voting options for up to 3 final element entries can have diverse redundant components. So it gives you a fair amount of flexibility. Okay, so at this point, I'm going to try and switch to the exSILentia demo. So again, see if we can bring the exSILentia demo up. So can you all see this? Okay, good. So again, for those of you that aren't familiar with exSILentia, when you bring it up, over on the left is the project information. So when you're creating a new project, you can put the project ID, you can put the project name, obviously the company, leader, etc. And here you've got the project options. So exSILentia provides you with these tools. You have process hazard analysis, you have select the SIL selection, you have SRS safety requirement specification, and you have the SIL verification and lifecycle cost calculator. So we have here the select and the SIL chosen. Over in the middle there's a dashboard, and this gives you a very quick overview of your project. So it shows you the number of units defined, the number of hazards defined per unit, in this case 3, your target SIL distribution, and this would have been when you do select, you set up your targets, and here you have a measure of what was achieved. So you can see it agrees, and here you have SIL2, and over here we have a TBD. So from the dashboard point of view, you've done all your hazards, you've evaluated all your hazards, but you've only done 67% of your conceptual design evaluation. So that's just a reminder that you've still got some work to do. And here are the life cycle steps that you can see. Hazard SIF identification, risk analysis, SIL selection, that's from the selection point of view. Conceptual design, SIL verification. Improved test requirement specification, that's in. Last week. These are just demo SIFs. If you come to the overview, you can see here that we created a SIF for an overpressure in the boiler and the consequence description here. Over on the right side, you can see we have our SIF information. We're looking at general information. We're in edit mode. In edit mode means that you can still go and make changes. Nothing's locked down. If you click on the drop down, you can see that you can have a review stage, you can have a closed stage or rejected, or not applicable. So obviously if somebody is doing an internal review of this, you can put that into the review cycle. If the design is rejected, then that can be indicated as well, meaning that they have to go back and start again. You can add here the session, you can add in team members, and you just click on the plus, select a team member, you click on that, you can put in a new team member, or you can select from a list if there's already a preloaded list, and then you'd have the name of the person, the email, company, title, etc. So all of this is very helpful for doing auditing. Any references, if you click on that for references, you can select a reference. Okay, so we got a boiler P&ID. Let's say that's one of the references. So now you can see that that's here. So all the references that you're using during either the selection or the design or even the PHA, so you can keep a complete catalog and any action items that need to be done. So this helps you with the management, it helps you with the auditing side. So if we go to the Silver tool now, you can see now we have a different representation, and it gives you a representation of the type of SIF. So you can see we have 3 sensors, 1 final element, 1 logic solver. Here we have the same, and if you double click on the icon, it brings you into the actual representation of the SIF. So here you see, here are the parameters, and then it asks you, consider architectural constraints, and we're saying we're going to use 61508-2010 tables. If you click the drop down, you can see you have choices. Here you could use the 1511 tables but ignore the 11.43 for type A devices. For those of you that are not familiar with that, there are 2 types of devices. Type A, which tends to be non-programmable, so it doesn't have a microprocessor or microchip in it, and type B, which does. Because with type B devices, you now have to consider the software elements as well. So you can choose which table you want. You can choose to consider 1508 systematic capability. So you click on this, you say yes, or if you say no, then you have to document it elsewhere, because 1511 requires you to look at systematic capability. The application test method, again, you can say here, it's either 2000 or 2010. The mission time in years, we have 15 years. You can change that up or down. And if you notice here, if I leave the cursor hovering, it just gives you a description. This is the period the SIF is operational from initial startup to complete refurbishment or decommissioning. So that's mission time. Startup hours. This is the time to perform maintenance, repair, clean up after a spurious trip. So you can set that. Demand rate. In this case, we're looking at low demand. You can have based on demand rate, high demand, or continuous demand. And now you have the graphic representation of our SIF. If you come down, you can see here, this is a representation of how much contribution to PFD average is there. Well, you can see the majority of it, in fact nearly all of it, is the final element. And that typically tends to be the case. The final element tends to have the biggest contribution because, again, a chain is only as strong as its weakest link, and the final elements tend to be the ones that have the lower PFD averages. In terms of here's the mean time to fail spurious contribution. Here, the final elements is not the main contributing factor, the logic solver is the main contributing factor. And then over here we can see what was our achieved safety and integrity level, 1. What was the achieved safety and integrity level from the PFD point of view, that was 1. From architectural constraints it was 2, and from systematic capability it was 2. So the average probability of failure on demand was calculated and the risk reduction factor noted. And here's our mean time to fail spurious in years, it's 20 years. So all of this information is calculated from the individual components, the sensor parts, the logic solver part, the final elements. And you can see that the SIL PFD average was 1, but the architectural constraints could be 3, and the systematic capability could be 2. So if we double click on the sensor group, now it shows us this is how we can define the sensor. You'll notice we have reused this group. This means that if you create a sensor group that you're going to be using or will be used over and over again, you don't have to enter the data every single time you create a new SIF. You just can say reuse this group, and you can see here it says already this group has been used 2 times because I used it in another SIF. If we come over here to beta, if you double click the beta, this is basically common cause modeling. Again, for redundant systems, you need to take into consideration the common cause aspects. And typically we default to 10% as a contribution, but you'll notice here you have separation. So you can actually say, all right, I have all my signal cables for the channels, they're all routed separately. The electronics for each channel are on separate printed circuit boards, etc., etc. You can click all of these if that's the case. And that will have, as you go through each of these tabs, here you have diversity and redundancy. You can look here at employing different principles for the sensing devices, for pressure and temperature. So in other words, if you have 3 pressure sensors, if they're not all from the same manufacturer and they're not all using the same type of measuring methodology, then you can claim diversification. Complexity, this is based on the techniques used in the equipment. Again, if it's been used successfully in the field for more than 5 years, you can take a credit for that. Assessment, manufacturers provided a statement the results of failure modes and fix analysis or fault trees have been examined. So again, you can if you know this information to be true, you can check these. Same with procedures, from human training, designers are trained, environmental, same thing here. So all of these, if you were to tick some of these, let's just take a couple. So yes, we've trained, maintained, procedures, yes, there's a written procedure. So we can say all of that. Assessments, yes, manufacturers provided that and that. Complexity, yes, more than 5 years. Diversity, let's say yes. Yeah. Separation, yes, they're separated, yes, yes. So now you can see our beta factor has dropped to 5%. So that does have an effect. So let's say yes, we'll use that beta factor. And sometimes that can have an influence depending, but it does need to be considered. So our mean time to restore is set at 24 hours, but you can see here it can be between 4 and 336 hours. If we come over to the left, we're looking at identical. In this case, we can say we're using diverse, because we said that earlier, we claimed that. And now you can see we have to put in the 3 difference. Instead of just one same device for all 3, we have to put in 3 different ones. Go back again. Yeah, you can say remove leg 2, remove leg 3, okay. So we're back to that. Advanced options. Here the failure rates are displayed in blue, and these are adjusted rates due to the PLC detection, configuration selection. So in other words, if there's diagnostics, if there are other things that can be taken into consideration because of the device you're using. Here we're using the Rosemount 3051S, and then this interface, the Pepperl and Fuchs interface. So you can see safe undetected, it gives you the safe undetected, safe detected in terms of failure rates, dangerous undetected and dangerous detected. So these can be filled in automatically by the fact that you've chosen to use devices that have been SIL certified, not necessarily by us, but we keep our database up to date with devices that are certified. And you can see that safe failure fraction calculation based on this data comes out to 91%. Our test interval, proof test interval here is 24 months. It can be 1 to 360. And obviously, if you're in low demand mode, you would want your test interval to be at least half So here we said 24, but let's say if we said 6 months, we were going to do that 6 months. Now you can see that the PFD average calculation changed. Our mean time to fail spurious has significantly improved, but we're still looking at SIL 1 simply because of the logic solver contribution and the final element contribution, mostly the final element because that is the lower. So for the measurement type, we're saying we're looking at pressure. You can have different types of detection of what you're looking to measure. You can define the service. It's a clean service. Here we have the rose mount defined and the petal and Fuchs defined. The types of options that we're looking at for trip, high, alarm, and over range. So those are taken in. Our coverage here, if you click on coverage, it says based on your current selections, the proof test coverage for 99% is achievable with the type of sensors and interface you've chosen. And in fact, it's clean service. So it asks you if you want to keep this proof test coverage. You can say yes or you can say no, and you can change that. We click on the logic solver. Here we're using the Emerson Delta V. We have the MTT out as set at 24. It's a programmable electronic system as the logic solver type. The proof test coverage. And if you click on this, the logic solver has a predetermined proof test coverage. So you can say OK. Proof test interval is 12 months. And again, you can reuse this logic solver, which I've done, so you can see it's used 2 times. If you click on the details and scroll down, you can see here, okay, it consists of a power supply. You have 16 IOs, and here they have all the failure rate information for the particular IOs. Also over here, if you look, maintenance capability of the sensors, you can say, is there none? Is it medium? Is it good? Is it perfect? We're looking at 90%, so it's good. Logic solver, same thing, you can set that. And for the final elements, you can set that. And then here's the safety equipment reliability handbook. We're showing all types at the moment that you could do here. You could do pressure measurements. So it gives you, so you can scroll down and so you can see which devices. And if you click on the device, it brings up the actual data sheet for that device. So you can see what the failure rate data is in terms of fits. And it helps you with your selection. Select failure fraction in this case is 67%. So that gives you a very quick method of looking at, okay, which devices could we use. And then if you click on the final element group, here we're looking at, again, this is being reused. We've got a single final element on this SIF, so we're doing a 1 out of 1. The interval is 12 months. Coverage percent, again, based on the current selections, proof test coverage is 69%. So you say yes or no, you can change that. Mean time to restore in terms of hours. And here's the type of interface module we're using. It's a remote actuated valve. You can have other or remote actuated valve. Here's the final element. If you have any pneumatic, you can put that in here. So you've got the drop down list, you can go through and you can very easily see. And you'll notice the bold versus non-bold. Bold means that they've been certified, and the non-bold means they haven't, or it's not known. And then you can say with my actuator and valve it's a combination or they're separate, and in which case you have to define that. And you can say is it open on trip or is it close on trip. Also, if you're using tight shut-off, if it's a tight shut-off required, you can define that. And if it's severe service, you identify that. If you're using partial stroke testing, you can identify that too. If you click on that and then scroll down, you can use the equipment data, or you can set the time yourself. Is it manual? Is it automatic? You can define all of that. And all of that feeds into the calculation engine and gives your overall SIL rating for the type of device. Here's another one where we've got the SIF, which is now SIL 2. Again, the same thing. We reuse the sensor group, so we've used that again, so it's automatically populated. See, the final element is different, so we have a better, I should say, PFD average, and we have achieved a much better SIL rating. Over here is the architectural constraints and systematic capability identified. And we have higher proof test coverage on this one. Higher coverage factor on this one. So that gives you a pretty quick overview on the exSILentia tool. We do have time for some questions. Let me have a look here. One of the questions was continuous updates of the equipment database. Can this lead to different results when using exSILentia? It can if the devices that you're using have had updated failure rate data. Usually, when we do the updates in the database, that can be changes or it can be additions. So if a manufacturer has published new data, or we've done a recertification, or somebody's done a recertification of the device, and there's new data, then certainly. But most of the time when we're doing the updates, it's either to add new devices, so that it shouldn't necessarily update, but it doesn't hurt to check if you think that might be the case. But again, when you open exSILentia, if you bring up your SIF, go into the Silver tool, you'll see if it's changed at all, because it's automatically, if the database has been updated, it uses that information. Another question. Can we use 100% proof test coverage factor for closed trip valve if the proof test procedure includes seat leakage test? You can always use 100% proof test coverage, but again, in our experience, you can never get to 100%. You can get to a reasonably high, and that's why when you look at the coverage factor, you can have near perfect or perfect. You can put that in, but certainly you can see if you've got tight shut off, and also you're doing regular proof test or proof tests. If you can claim that your coverage and your proof testing will get you to that point, then of course that's entirely up to you. But we tend to say that you cannot achieve 100% proof test coverage. Is partial stroke test an option or is it strictly required? No, it's an option. As you saw, you can click it to say you can do partial stroke test. All it means is if you're doing partial stroke test, you'll get credit for doing that, and that will help improve your test, your proof test. The voting configuration, is there any difference in the calculation if they're all entered within one group and if they are entered as separate groups in exSILentia? Well, as you saw, I entered one sensor group. You can enter separate sensor groups, but again, the voting here, you can see voting is 2 out of 3. even if you had different sensor groups, you'd still have to do the voting. Now, whether it was 2 out of 3 or whether it was 1 out of 4 or whatever it was, of course, you still have to do that voting. You still have the constraints associated with that. Let's see if there's any other questions. Any more questions? Okay, well, I thank everybody for attending. Sorry about the little delay, minor delay getting started. This session has been recorded, so you can always go back and revisit it. You will get links, and you'll get copies of the presentation slides, so you'll see that shortly within the next day or so. If you do have other questions, feel free to email me. My email address is sgandy@exeter.com. I'll be happy to answer your questions. I hope you found this useful. I know it's difficult in an hour to go through what is obviously a lot of information that's here in the tool and the capability of the tool, but hopefully it gives you a good idea of how you can use it. It does save you an awful lot of time, and that's one of the big pluses, is you can enter the information fairly quickly, you can verify your design very quickly, and you can create reports as well, and you have a full audit trail. That's the other thing that's very important, because in 1511 you have to provide an audit trail to show your process and your decision making and your any deviations or any reasons why certain things were changed or done. So with that, I thank you all. We will be repeating this session at 4 o'clock this afternoon, US time. So with that, I bid you a good day or good night, wherever you are, and thank you for attending.